settle down and get ready for Okay, all right. Welcome everyone back to our first invited talk. Well, extremely happy to have Iftach Haitner as our invited speaker. And Iftach is a professor at Tel Aviv University and cryptography at Coinbase. His research has won a SIME Outstanding Paper Prize, a Crypto Best Paper Award, and a ERC grant. Iftach's research primarily focuses on cryptography minicrypts, making sure that the world is a safer place, even if public key cryptography doesn't exist. All right, let me hand over to Iftach now. And thank you for joining us at TCC.
So, use this mic, I have an angle mic, or this one? This one. So, hello everyone. So first, I would like to thank the committee for inviting me. TCC is my dearest conference, the first conference I ever sent paper to, the first conference I ever have a paper published in. I have a funny story about this first conference, first submission. So I wrote my first submission by myself. Oded Goldreich was my advisor when he was away. I wrote the worst written submission ever. Luckily, it got accepted. But then one of the reviewers basically said, it's a very nice paper, and politely, it explained me how to write it. Really, it really gave me the text of the abstract, for instance. I just copy-paste the abstract. I said, wow, this is great submitting papers. Everyone, like, you write whatever you like, and people just tell you how to write it correctly. So it wasn't like that since then. And the reviewer was, of course, Yuval Ishai. I didn't know him back then, but afterwards he introduced himself. So thank you very much. So I'm going to speak about coin flipping, but before that, I feel that something non-scientific. I think that as an Israeli, I cannot give a public talk these days without mentioning the Hamas attack on Israel. In particular, there's something like 150 people still in captivity, including elderlies, including young kids. So I hope these people will be back soon. And I hope that there's going to be a peaceful solution to this area soon. Okay. So now let's go back to science. So coin flipping. What is coin flipping? Very simple protocol introduced by Blum back in 81 in this paper. Coin flipping by telephone, people used telephone back then, a protocol for solving impossible problems. I guess what Blum would say about what we do now in crypto. And the task is very straightforward. Two people want to flip a coin over a phone, they distrust each other, and want this coin to be as close to uniform as can, even if one of the parties cheats. So this is exactly what I said. And let's see a very simple example for such protocol, or attempt to such protocol. So Alice flips a bits. A pause. Please ask him a question. You can do it online. Not too many, but I know how to manage it. So it's not a 15-minute talk. It's a 1-hour talk. So you're very welcome to ask questions. So Alice flips a bit and just sends it to Bob, and both parties output the result, right? So on one end, both parties are both honest. In an all honest execution, the output is uniform bit. But clearly, if Alice cheats, she can make Bob output 0 with probability. Whatever measure you use, it's not a good coin flipping protocol, right? So in the same paper, Blum introduced good coin flipping protocol, which goes as follows, the famous Blum coin flipping. So Alice flips a bit and commits to the bit, send it to Bob. Bob flips a bit, send it over to Alice, and he commits, and both parties output the XOR. So it seems that even if Alice gets corrupt, nothing much she can do about it, right? I mean, because even if she, like this, so even if she say always commits to 0, because Bob commits to uniform, to uniform bit, the XOR going to be uniform. So is it a good coin flip? Well, it turns out it depends how you define the security for coin flipping. If you only require security with a board, namely you allow the honest party to abort if it detects cheat, then it is negligible bias. Namely, Alice cannot make Bob output 0 or 1 with probability which is significantly larger than 1. But if you require the honest party to always output some bit, which is important in some setting, we call it fair coin flipping, then it's not hard to see, I'm going to address later in this talk, that whatever Bob does in case of a cheat, Alice can abuse it to bias the protocol by, say, 1 bit. Okay, for the first type of coin flipping, which is security with a board, I'm going just to call coin flipping, which is the modest security definition. And for the second one, which require the honest party to almost also bit, we're going to address as fair coin flipping. Okay, I'm going to give more detail about these two definitions. But before that, why should we care? Okay, we have like 55 minutes, I think, to speak about coin flipping. Should be important, right? I mean, why should you care about coin flipping that much? That would require 55 minutes. Well, I was invited because I said I'm going to speak only about coin flipping, so maybe, but still, I think it's worth the time. So, coin flipping is a fundamental primitive in cryptography, not only in cryptography, also in distributed computation. It allows us to parties that distract each other to create public randomness. Less clear, it's related to stability of random processes, which is unrelated to coin flipping. But the actual reason for which we should care about coin flipping is that as a computer scientist, as a theoretical cryptographer, we try to understand computation. And a very important resource in computation is interaction. Okay? We know that we can do things using interaction, like zero-knowledge proof, like multi-party computation, and other things that you cannot do without interaction. But why is it so? What is so important? Why is so good about interaction? Give us additional power. Coin flipping is the simplest protocol one can imagine. There's no input, there's Boolean output, okay? And still interaction is crucial for coin flipping. We see it in this talk. So this is a right playground to deeper our understanding about computation, specifically about interaction computation. It is the way I see it. Good. So what I'm going to talk about, I start with the complexity of the simple coin flipping, namely without a board. This is related to what you call minimal assumption for cryptography. Okay? What requires minimal one function, what does not. Then I'm going to switch gear to fair coin flipping, security without a board, which clearly relate to fairness cryptography, but also to the tension between minicrypt versus cryptomania, what we can do using only one function, and what requires public cryptography. And finally, I'm going to speak shortly about full information coin flipping. This is a non-cryptographic object. It has nothing to do with cryptography. Its main task is distributed computation. Surprisingly, it leads to attacks on such coin flipping, leads to attacks, poisoning attacks on learning algorithm. I'm going to touch upon that. But still, even though it's a non-cryptographic object, parties are unbounded, etc. There is some thread that connects all of this work that I'm going to present here and see it today. Good. So let's start with the first topic, which is complexity of coin flipping. So for natural reason, I'm going to speak a lot about works that I did, not only, but a lot of. And I did these works with great colleagues. And this part of the works I did with Itai, who is back then my student. Eran was my postdoc. And Arif was my visiting student. Good. So let's be a bit more formal. So two-party coin flipping is a efficient protocol between Alice and Bob, such that in an all-honest execution, the output is a uniform bit. And even if, say, Alice is corrupt, is polynomial bounded, is corrupt, it trying to make the output to be, say, 0, she cannot make Bob output 0 probability, which is larger than 1/2 plus delta. Okay? Note that honest party can abort. Okay, so I allow cheating allies to make Bob always abort. Okay, I'm not counting for it. I'm only measuring the probability that Bob will output 1. Okay, this should be not significantly larger than 1. We consider negligible and non-negligible delta. Delta might be constant or function of security parameter. And note a bound, I'm going to focus on low bounds. So bounds in the two-party case extend naturally to any number of parties as long as we don't assume condensation. Okay, so this is the basic definition. Let's make sure we are on the same page. So a zero bias coin flipping, is it a good one or is it a bad one? Good. This is perfect coin flipping. It means that a cheating party, cheating Alice, for instance, cannot make Bob output 1 with probability which is larger than 1/2, and cannot make it output 0 with probability is larger than 1. What about 1/2 bias coin flipping? Not Chris, someone else? I've been a teacher for too long. Right, this is trivial coin flipping. It means that cheating Alice can make Bob always output 1. Good. What do we know about the complexity of two-party coin? So the ultimate goal is to prove the non-trivial. Non-trivial is the protocol. You can almost fully bias it, but not completely. It is 1/poly far from 1/2, implies 1 function. Why 1 function? Because by Blum, we know that 1 function implies such point. So first observation, which is rather trivial, that non-trivial coin flipping implies p-space is not in BPP. Why is it so? Because there is a simple p-space algorithm that totally breaks a coin flipping. So if p-space was in BPP, there was an efficient attacker that totally biased coin flipping protocol. Less trivial is observation by Zakos by 86, which basically it follows from a general result. By Zakos, you probably essentially prove that for constant round protocol, the same old but a stronger implication. NP is not in BPP. Then in the seminal result of Luby, we finally got the right conclusion, which is coin flipping plan 1 function, but this only holds for very strong coin flipping, almost optimal coin flipping. 1/r bias. You can only bias by 1/r when r is the round complexity. Then there was a long pause, actually a 20-year pause. There was no advance in this on these bounds at all. Then in Pagliazzo 5 words workshop in Princeton in 2009, I think it was Monet, said, look, there is an important question that you don't know how to characterize, whether coin flipping is in minicrypt or even maybe in Pessilem. Okay? So some people were listening to Monet, not me. It was Maggi, Manoj, and Sai. And a year later, we proved the following result. We proved that a quarter bias coin flipping, namely not very good, but not very bad as well, does not imply 1 function, but implies the NP is not in BPP. Somewhere in between. A year later, with the random read, we proved the following result. Also constant bias, not as good bias as a better bias than here, but still constant bias imply 1 function. Okay, so the conclusion is correct. The assumption is still, it's not a non-trivial one, it's a constant bias, somewhere in the middle between trivial and not. And this constant might be arbitrary, but it turns out this is exactly what you achieve using quantum computation. If you are allowed to send qubit, then this is the best, and you can do coin flip information theoretically secure. Okay, exactly the same bias. So for a while, we say, wow, found a very exciting connection between what you can do using 1 function and what you can do information theoretically using quantum. But it turns out it was only artifact of the proof. And 3 years later, with the Itai and Aris, we proved that we almost closed the question, namely almost half bias. We call it half bias, it's trivial, constantly small to half bias coin flipping implied on 1 function. Okay, it's not the end of the story because we still, for you to prove, they still need to prove that any non-trivial, namely 1/poly far from 1/2, not constantly close to 1/2 implies. Okay. So let me speak about this result. This result, the proof is, you're going to see, or hopefully agree that it's very simple. I can explain it in a few minutes. I try to do it. And so what actually should prove? Should prove the following. This is a general paradigm for proving that something implies one function. For any protocol pi, coin flipping protocol pi, we should identify an efficient function such that either it is one way or there exists an efficient adversary that bias pi by exactly this quantity. Okay? So if this protocol is a good coin flipping, one function exists. Not only one function exists, we can really write down what the function is. Okay? It's constructive construction of one function. Okay, so this is what we should do. You give me a protocol, I'm going to identify a function and say this is one way. You say it's not one way. I say, okay, if it's not one way, I need to show you how to attack the coin to break the function. Which function to use? Any idea? I'm giving you a protocol. You see the protocol description. Which function should I use? Turns out that always what the function is, what the candidate one function is, it's always trivial. In protocol, it's going to be always the transcript function, namely the function that takes the coins of two parties and output the transcript. The function is always trivial in almost every time they will try to say this implies the one function. What the candidate function is trivial because you don't have much room. What can you do? You have a protocol, you should come up with a fluid function. The other part is proven that this is indeed a one function. Okay, that if this is not a one function, you can use it to break the protocol. But what the function is, it's trivial. Okay. Some notation, be light on notation, but still. So we're going to use a two-party coin flipping as a representation. Naturally view it like that. You know, like the messages are just bits. For simplicity, assume that the messages are bit. If they are not bit, we're going to partition the protocol into many rounds. So, you know, that's the convention. It's not going to be very important. If A sends 0, we go in here. If A sends 1, we go here. Nodes are the transcript. I'm going to identify node with the transcript. So this transcript, this node is just the transcript 0, 1. This clicker is terrible. I warn the future speakers. Inner node labeling, add a label to inner node whose party controlling the node. So Alice send the first node, so she control this node, and Bob send the second node, so etc. etc. Leaf label is going to be the final output. I assume with also generality, the output is written on the transcript. If the label of the leaf, that's the output of the protocol induced by the transcript. Edge label is not very important. What the probability of taking this edge. And this is the only important notion you should remember. What is the value of a node? Something will address it as the game of the value, the value of the game. This is the probability of hitting one leaf, namely the protocol outputs one once in a node. Let me be more explicit. I'm assuming I'm in this node, the transcript is 0. What is the probability that if you sample random coins for both parties, condition that you are in this node, that the final output of the protocol is going to be 1. Okay? This is a node value. Probability. You see partial transcript of protocol, you do random continuation of the protocol. What is probability that you output? What is probability to reach a 1? This is the only important definition or notation you should remember. Node value or game value. So how to attack? I have a protocol I need to attack. So all-powerful recursive attack, which is always very successful, is out of the question. It's not even NP. So we first know that if the transit function, going to be more formal about it later, is not one way, so for each node, we can compute its value. We can compute the probability that if we continue random commutation of the protocol, we're going to output 1. Not only then, we can only sample a random coin leading to this node. Okay. So what should we do with it? So here's a natural approach. What we do with this point to be greedy. So A plays the first round. He should decide whether to set 0 or 1. It computes the value of these two nodes, Namely, what is the gain value? What is the probability of outputting 1 if you send 0 and if you send 1? And what it does, you want to output 1, say the probability if it reaches this, if you send 0, it output 1, it's 3/4. And if it reaches this node, the output 1 is 1/4. Which message should descend? 0. Right? It's called the greedy approach. Is it a good attack? Turns out it's a very bad attack. You can come with example for which neither Alice nor Bob can bias the protocol by playing. So I'm going to describe you a different attack. It's called the bias continuation attack. But I'm going to describe it soon. But what's important about this attack, and this is maybe the one take-home message, I'm going to repeat it for this talk. When you're attacking interactive protocol, what you should do. So in one line, you should act gently. Okay? When you play interactive protocol, you play many times. It's not a one time. It's not like in the walk by Hillel. Before Hillel said before that you have a function, you have to invert it once. You have to do something bad once. No, here you have to attack many times. And if you're not acting gently, for various reasons, in many settings, different reasons in different settings, it's not going to work. You have to act gently. You want to get one, but don't be too blunt about it. Okay? Just slowly push the protocol. There is one approach to doing that. The bias continuation. We're going to describe the bias continuation of A towards 1. It's analogically defined towards 0, and analogically defined for B. So what it does, given a transcript, Alice of A, cheating A, sends uniform coins for both parties, not only for him and for both, that are consistent with the transcript that far. Namely, if both parties plays with these coins for, say, 5 rounds, we're going to get this transcript, which is after 5 rounds. And the final output of the protocol with this coin is 1. Okay? And then, after doing that, it takes his part of the coin and acts according to his part of the coin. Okay? He sample random coins linked to these nodes that final output is 1 and act according to his part of the coin. Animation will help. So here's Alice. First round, just sample random execution of the full protocol. And this execution leads to 0. So what he does, he resample the point. And now, again, for both parties, full execution is defined, he gets 1. This is great. He plays according to the first message. Now with B's turn, B is honest. He does whatever he likes. Now Alice A turns again, he sample random continuation of the protocol, got 0, sample again, got 1, and now he acts according to his code. Okay? So B is analog defined. Note that Alice is almost honest. You know this joke about that you went to the shop and bought 2 cones of ice cream, and one of the cones fell on the way, and you come back to your friend and say, sorry, your cone is fallen. You know, you're almost honest. One of the cones is fallen, but who decides whose cone is it? You, right? So you're only slightly cheating. You're almost honest, but unfortunately, the random coins end up in 1 and 1. So bias continuation used also elsewhere. I first noticed this, I have read about this stuck in paper by Assad et al. And part repetition. I'm pretty sure people told me it used before, but I don't have an exact reference for this. So if first time it appeared in Assad et al. Paper, so I apologize for that. Good. So here's the claim. How good is this claim? It's a very simple claim. It says the following. Either Alice attacking Bob or Bob attack Alice achieves the right bias. Okay, the final outcome is 1 over square root of 2. Therefore, the bias is 1 over square root of 2 minus half, which is what's in 2. Okay? And actually, this also holds for 0. So there's attack toward 0 and attack toward 1. It might be that Alice managed to attack both directions. It might be Alice one direction, both the other direction. This the claim does not say. Is it clear? A very simple attack. I'm not saying it's efficient, even if one function do not exist. We're going to get to that later. It's a very simple attack, you know, and very simple claims. Okay, and it turns out that also the proof is going to be rather simple. Let's see. So first observation, which is almost trivial, but in some sense it's the crux of the proof. Consider what happened if both Alice and Bob use bias equation attack to get one. Doesn't make sense, right? But still, you're both cheating towards one. What are you going to get? One. We're both cheating towards one. We're going to get one. Not surprisingly, actually, we're going to get a uniform output, a uniform transcript leading to one, but it's not very. Second claim is some more subtle. It says the following: for any frontier in the tree, for any cut in the tree, but if it confuses you, the word frontier feels about for any node, the probability that an all honest execution reaches this node times the probability that an all cheating execution reaches the node exactly equal the probability that on A cheats it reaches the node times the probability on B cheats it reaches the node. Again, you can think what happened when both party cheats times what happened when none of the party cheats equals for every transcript what happened Alice cheat times the probability what happened what Bob cheats. And how to prove it? Exactly right itself. Okay? We just note that the probability of reaching a node is the product of what A does times what B does, what A does and what B does. It's like Markov chain. There's no connection between the probabilities. So that's the proof just right itself. That's all. Okay? And therefore, because this is a product of probability, you can mix them together. That's all. We are done. So now it follows the probability that cheating A gets one. One is the on one list, so it's a frontier in the tree. Time probability cheating B reaches one is 1/2. Why is that? Because in an all honest execution, probability getting one is 1/2 because this is a coin flip. And the all cheating probability getting one is one. This is what we said before. So this is 1/2. It's 1/2 times one. So this is 1/2. Therefore, this is the proof, and therefore we are done. If this product is 1/2, it means that either this is larger than 1 over square root of 2, or this one is larger than 1 over square root of 2. This is the whole proof. I'm not cheating. I maybe shorten the proof, but there's no cheat here. Okay? Good. So the bias contention attack really does what it should be. Is it efficient? Okay. So remember what we should do, what the bias contention does. Given a transcript, we need to sample coins such that are consistent with transcript and the output is one, right? So we want to use for that a one function inverter. Remember, we assume that transcript function is not one way, and therefore we want to use a one function inverter to implement this attack. So it's a bit more subtle than that. We consider the following function. It takes the coins, but it also takes the round index, and it outputs the transcript till the ith round and the final output. Okay, and then it's the transcript function concatenate for specific round and the final. Similar result manipulation will shows that says that either f is one, slightly cheating, but not more than that. Either f is one way, or exists efficient inverter that not only invert f, but it returns random pre-images. Okay, so it seems that we are done. Okay, all we need to do to sample the randomness that leads to one, we should call the f inverter on alpha and one. So we're going to add transcript not only consistent with alpha, but also the final outcome is one, right? The subtlety is that the fact that f is not one way, it doesn't mean, actually, it really doesn't mean that the f inverter works on any distribution. F inverter might fail, but on the typical output of the function, it should work well. But are we calling the f inverter on typical outcome? First time we do, we are. But A continuously biasly, A attack many times. This is one of the hard things of attacking interactive protocol. You bias the protocol, and then you bias it again, and then you bias it again, and then you bias it again. So we have no guarantee about the distribution in which you call the F inverter. Is it clear? It's not happening in non-interactive protocol or not interactive feature. You attack once. When you're attacking many times, this is one of the issues you should deal with. So there actually are two types of non-typical queries. One of them is really one that you give them very different distribution. The second type, which they are typical, but this transcript are very likely to output 0 if you are in this transcript, but you want to get a preimage of 1. Nevertheless, you can prove the following, that attack does good enough, even if it totally fails on non-typical nodes. Good enough doesn't mean it does as good as the bias quantitation. You can come up with a protocol in which the bias quantitation does much better than what we claim, but still the attack does essentially what the claim bound. Okay? And the reason is, the proof is not trivial, but also not that complicated. It follows essentially from the same two claims we said before. In particular from this, what the frontier claim that we said. Okay, this is the gist of the proof. Okay. Question? Yes. No, so the reason is that our attack was what I say symmetric, was very symmetric. You know, both you can attack to 0 and to 1, and this is for this reason we got stuck in the quantum bound. When you give a non-symmetric attack, so we went out of quantum. But this is what quantum guy told me, basically. Good. So this was I'm not going to be that technical in the rest of the talk, but let me say that so first mentioned that with Itai and Aris, we went almost all the way through the recursive Bayesian qualification attack, whatever it means, did pruning in the head attack, but whatever. This is the end of this talk. Okay. So now, if you lost me in the previous section, total new section, okay, fair new people. So I go the wrong direction. So new people, Amos sitting here, Niv, Nissan, Nikos, Eliad, now was a student, now postdoc, and Eran. Okay. I don't know what this step is, but it appears from when I switched PowerPoint. Good. So what is, again, new topic, okay? If you lost me, you can join me, ask me back again. Again, what is the fair coin flipping? It's a coin flipping like before. We call it delta fair, not delta bias, but essentially the same definition. But the difference is that the honest party always owes a bit. It never aborts. In many settings, we would like to have a fair coin flip, okay? Me and Chris want to go to a movie, we flip a coin, and then Chris aborts. But, you know, I don't want to punish myself and stay at home, right? I want to go to a movie. So I'm going to a movie, so this allows Chris to bias me, okay? Because if I'm going to flip a coin, by aborting, going to cause me to go to a movie, which I didn't like. Okay, not to a uniform movie. Good. So fair coin is flipping in the sense the right definition. Okay, so let's see why it's more complicated. Again, this is Blam protocol. You know, like I said before, it's great. You know, like, you know, and this is the protocol, it seems fine. But now Alice performed the most devastating attack in cryptography, which is abort, right? You can force the adversary to act honestly, to flip coins as it should, to act according to the protocol function. But we cannot prevent him from aborting because it's a valid action. Maybe he really aborted, maybe there's a network for it. So what? Alice does the only, Alice plays perfectly honest. You want to get one. She knows the outcome now, okay? She knows it's going to be 0. What's she going to do? She's not going to open it. So what Bob can do? If he flips a coin, Then what is probability of 1 now? The probability the original protocol was 1, which is 1/2. Now the probability that the flip uniform coin is going to be 1, which is again 1/2, so it's frequent. It turns out whatever Bob do, there's no way for Bob to choose his output in case Alice abort that prevents a bias at 1. And actually, it's more general than that. Cleveland, a beautiful result in 86, proves the following. For any R-round protocol, a fair coin flipping can be biased by essentially 1 over. So let me say something about this proof. So consider the following graph. So the x-axis is the round, the round identifier, and the y-axis is the gain value, what we call node value. Given the current transcript, what is probability of outputting them? So consider one specific execution of the protocol. You know, the gain value at the beginning is 1/2. Why is it 1/2? Because this is the coin flip. Before you start, the probability of outputting 1 is 1/2. And when it ends, it's either 0 or 1, because the transcript contains either 0 or 1, right? The part is output either 0 or 1. So you don't have to be a great mathematician to note that if you went from 1/2 to 1, you have some a gap between 2 consecutive rounds, which is at least 1 over r. Right? Good. But does it imply an efficient attack? So not necessarily. We can say the following about the previous type of coin flipping, which is non-fair. Also, there was a gain value of 1 over r. But there, if one function exists, we cannot exploit finite. What makes the difference here that this is a fair coin flipping? Namely, the fact that both parties always output a value. It's a subtle point. Why does it help? So the reason is that, you know, the protocol provides you what we call defense value or backup value. The protocol will tell you what to do if the other party aborts in the second round. The protocol tells you what to do. Should output 1 or output 0. Maybe you apply some complicated function, but you should output something. That the protocol instructs what you do in each round if the other party aborts. It turns out this is a very short proof, but it's very confusing, that you can use this very defense value to perform an attack. Okay, it's not trivial, short, but not trivial, but this is the crux. So this is one of our attack. Yes. Secret information. Yeah, to compute the difference values on secret information. Yes.
So regarding the previous example, shouldn't the bias be 1/2? Because I commit to my randomness, I get the other value. If it's what I want, if I want 0, if it XORs to 0, then I decommit. If it XORs to 1, then I abort. And this would like give you the perfect.
And then what the other party does in this case. So if you're referring to the previous example, to what the yeah. One second. So what the other party does, what Bob does in case Alice aborts, I assume he flips in from there. You can instruct him differently, maybe to always output 0, and then have a perfect attack towards 0. I always abort and you always output. Whatever you do, doesn't.
Thanks.
Okay. So we said that we cannot do better than 1r. Let's try to get there. Let's start 1 over square root of r protocol. This is a protocol by Avrohur et al. No one admits he ever written this protocol. Cleve referred to this protocol in his law one paper, but no one asked, I think Gabi Bracha, one of the authors, said, I don't read. It's never published, okay? But it's simple protocol. So here's the protocol. Basically what it does Blam protocol for r times. Okay, independent coins for r times, and then the output is the majority if there's more 0 on 1. But recall, we want to build a fair coin flipping. What should we do? What Alice or Bob do in case the other party aborts? What Bob does, Alice, analogously, if A aborts at round I, what Bob does, it samples CI by itself, but also the rest of the coins, and output the majority. Namely, basically, it samples from here by himself. Know that this is an attack opportunity for Alice, because Alice sees that the ith round CI is going to be 1, but she wants to get 0, so she aborts. Bob going to resample CI, and therefore CI might be 0 as well. It is an attack, but not as good as attack as before. Okay? So how good is this protocol? How fair is this protocol? The answer is 1 over square root of R. Why? No basic fact about independent random variable, that if you change one coin out of N, out of R, you buy the probability that it's going to be majority 1 or 0 changes by 1 over square root of R. Okay? Anti-Chernoff. Okay? So there is highest and bias, but 1 over square root of R. Okay? Very simple protocol. 86. Are there better protocols? For many years, for 23 years, people didn't know the result. People actually thought, for the reason I'm going to say in a few slides, that this is the optimal protocol. Some people, including me, try to prove it, that this is the protocol. You cannot bypass 1 over square root of R until Moran, Naor, and Segev, their breakthrough in 2009, not. Assuming OT, oblivious transfer, you can do much better. Actually, you can match Cleve-Lorber, which is 1 over R. This is not the protocol. Actually, it's a variant of my and Eliad protocol, which we built for free parties. But the gist of the protocol is what they're understanding. Okay, very nice understanding. So what you do, you start with our protocol, but before each round, the party do the following. They send their randomness, their coins for this round to a trusted party. The starting party compute the game value at the end of this round. Namely, it computes CI. It knows AI and BI, can compute CI. And compute delta I, the probability that the protocol output 1 given also CI. Okay? It knows something that both parties don't. And then it sample a coin according to this distribution. Namely, it's 1 probability delta. And it sends it only to Bob. Now, if Alice aborts, Bob output is DI. Now, it's not out to see that Alice cannot attack at all. Because if it aborts, Bob output a value which expected output exactly after the jump, after the information that Alice learned. So Alice cannot attack. So is it a perfect coin flipping? No, there is no perfect coin flipping. So who can attack if Alice cannot? Bob. Why Bob can attack? What allows him to attack? In the previous protocol, he could not attack. What allows him to attack in this protocol? DI. He learned DI, and DI is information about CI. But he didn't learn CI. He learned noise information about CI, which is a sample according to the game value induced by CI. And one can prove that this information also gives him a bias of 1 over R and not 1 over square. Okay? So we enhance the protocol with additional machinery that push down the bias to 1 over. And by the way, you implement this trusted party using multi-party computation with a board. Simple, not cheating. Good. So, so same gap between 1 over R and 1 over square root of R. So as we said, 1 over square root of R protocol you can construct using only one-way function. 1 over R, you need OT. Okay, so we start asking ourselves, well, is it really the case that for 1 over R you need OT? And again, Cleve showed that 1 over R is the optimal, but Cleve and Pagliazzi prove actually a very interesting result. They say that if the game value is efficiently computable, then you can bias any coin flipping but 1 over square root of. Okay. And follow from basic factor Martingale, and then Maggi and 1 following result by Soled and et al., include Tal sitting here, prove very how to prove result. In the random oracle model, you cannot do 1 better than 1 over square root of. And actually proved also in the PKI model, where you have like idealized model of public key. So does a protocol that is better than the trivial 1 over square root of R, the requiring one function, applies OT? It's not clear. If you think about it, I mean, what the heck? I mean, how do you relate like small bias to something which is public key cryptography? I mean, the other way is no, that OT implies 1 over R, but the other way around is very mysterious. Why the connection is? And let it just one line. So if you think about public key cryptography, not as a mean to construct public key encryption, for instance, but if you define public key cryptography as a non-trivial correlation between the parties, a correlation that is not understood from an outsider, and then you go back to the protocol from Moran and see that exactly what allows you to go to 1 over R is non-trivial correlation between the parties' views. So you understand that there should be a strong connection. Okay? Namely that to get below 1 over square root of R, you need non-trivial correlation, and this non-trivial correlation hopefully can be purified to get you over. So in a work with Nikos and Eran, we proved the following. We didn't do all the way through. We proved at least for constant round protocol, a non-trivial coil flipping, namely little o of 1 over square root of R, implies Kierkegaard. Not OT, but Kierkegaard. OT is very hard to beat. Kierkegaard is much easier. Okay. Good. So, how much time do we have? 10 minutes. I'm going to skip the proof, this result. It's not the proof, I just want to say something about it. That's mentioned, there's only a lot of literature about many party coin flipping, constructions, and attacks, which I'm going to skip. So for the last part of the talk, I'm going to do it very short. I'm going to speak about full information coin flipping. This is a joint work with my student, Jonathan Teridian. So what is full information coin flipping? Again, if you lost me till now, wake up. Totally new object. So this is the most simple coin flipping one can imagine. First, the only communication is done via Blackboard, via a single broadcast channel. Okay? Every time party flips coins and writes his message on the Blackboard. Go on. And then a common function is applied to what written on the Blackboard and output a value, either 0. And again, some party might be corrupted, and now said what happened if some party is corrupted? Can they bias them? It's slightly more formal. Again, this is introduced by Boehner and Lineal back in '85 for what meant sending it. So communication is solely over a single broadcast channel. Every round consists of a single party with also generally predetermined to send the message. Output is an intrinsic function or transcript. Everyone agreed on the function, and when the protocol ends, they apply the function. Adversary is computational bounded, no crypto. Okay. I said that such protocol is still resilient if no T-corrupted party can fully bias the protocol. We are very rough here. We don't care, but it's still resilient if you cannot bias it almost completely. It's still resilient. And note that if we focus on single-term protocol, in which every party sends a single message, this is closely related to the study of Boolean function. Namely, the question translates to, by changing T input of the function, can you control its output? Can you fully control it out? Is there a T junta? Okay. Before stating the results, there is a very interesting connection made by Malajoufi, Jifar, and Mahmoudi. Says the following. So it's nothing to do coin flipping, it's nothing to do full information coin. Consider learning algorithm. He tried to classify his DNAs found somewhere, tell whether there was a rabbit there or a giraffe. Okay. And some adversary is coming along. He tried to convince, he has some incentive that we think there was a giraffe there. Okay. But yes, he cannot mole all the samples, he can mole some of them by paying some guys to change the samples. I think the samples coming from different places. The question, how resilient this learning algorithm is. Or can you make a learning algorithm that is resilient to an adversary changing some of the samples? If we change all the samples, we are dead. But you can only, if you only change some of them. Think that the classifier is only Boolean circuit, and DNA samples are eventually binary strings, and giraffe and rabbit also, like, you can map them to 0, 1. This is just full information coin flipping, okay? Samples coming in, we need to decide what to output to 0, 1, assuming that a random sample will output 1. Okay, actually, this can be made formal. Mahmoudi, M&M really prove that, okay? They translate an attack on full information coin flipping into a pointing attack on learning. I'm going to say nothing about it, that was a teaser, read this paper. Okay. So I have 5 more minutes, right? So let me introduce the most simple full information coin flipping there is. Each party sends a single random bit and you take the majority. Okay? It's not 2 parties, it's n party. Each party sends a single majority. And it's easy to prove that this protocol is resilient to square root of n. Okay? If you know, basically by chairness. If you corrupt more than 3 of parties, you fully control the. It's more than square root of n of the party, you fully control the result. If less, you can do nothing. Okay, so the most naive protocol. Are there better protocols? Okay, think about full information conflict, unbounded parties, single blackboard. We should design a protocol. Are there better protocols than the stupid n majority protocol? What do you think? Yes? No? Depends. The answer depends. What kind of adversary you consider? If it's what's called static adversaries, you have to decide on the adversary before the protocol starts. This translates to, it's very closely related. In some sense, initiated the study of Boolean function in computer science. And turns out for static adversary, you can do way better than majority. You can do all linear number, protocol resilient to linear number of collisions. Okay? You know, great names, writing great papers. I'm not going to speak anything about it. Okay? But this is what you should remember. Essentially, they're very good protocol, way better than the majority. What about adaptive adversaries? This adversary can decide who to corrupt during the execution. One certainty, he has to decide before seeing the message sent. Okay, but you wait before each time a party sends a message, he can decide to corrupt it. He has a limited budget, but can he decide it through the execution? So first, does it make any difference? So here's an example of it does. Think of a protocol, which is a very good protocol for static corruption. You decide on a small committee, say square root of n, and then the committee does the majority. This is a very good protocol for static adversary because they don't know in advance who's the committee going to be. Adaptive adversary is very bad because they wait till the committee is selected and then they corrupt all the committee. Okay? Good. So what do we know? The only upper bound we know is the stupid majority. So the goal was to prove this is indeed the optimal protocol. And it was a long chain of papers. So square root of n is optimal for first proved by Lichtenstein, Lineal, and Sachs for single bit, single tail protocol. I mean, every message is only a bit, and each party sends a single message. Then it was proved for symmetric single turn by Goldwasser, Kalai, and Park. Symmetric means that the output function is symmetric, dependent of you can permute the inputs. It doesn't change its value. And 5 years ago, Kalai, Komogowski, and Raz proved that it's true for single turn. So as long as one party only speak once, you can square root of n bias suffices. And finally, with Jonathan, we fully proved the bound, namely any protocol can be biased by corrupted square root of n parties, or in other words, majority protocol is the optimal protocol for adaptive. So I guess I don't have time to go into result. Or I do. I don't. I do. How much time do I have? 5 minutes. 5 minutes is more than enough. Good. So something about the proof. I'm not going to give you the proof, but that's something. But I want to relate it to the attacks on I'm going to present an attack. I want to relate it to attacks on the very second attack I did on coin flipping for one function. So it seems unrelated creature, but still. So let's do how to attack single tail protocol. Okay, single protocol, every party speak once. You again, what you do, you consider the what's called the gain value, the difference in the gain value between two rounds. So JK or J is just the difference in the gain value, the jump in the gain value between consecutive rounds. So every round there's a new transcript going on, a new message, and compute what is the gain value between one and what you care about the difference between the difference in the gain value. What we said that cleave proved that there's always a jump of 1 over n, and actually by cleaving Pagliaccio there's a gap of 1 over square root of n, but maybe it's not exploited. And what Kalai-Komodowski and Raz proved is the attack is very simple. So every time you see a jump, you take it. Okay, every time there's going to be every time basically you see you see there's going to be a jump, you're going to take it. Okay, you can say something in advance that the next, essentially you can tell that the next method is going to induce a jump, or the next method has a possibility to have a jump. Then you corrupt the party is going to send this message and corrupt it to the direction that you like. Okay, and that terms will be suffice. Again, your greedy approach suffice. It's very similar to those who are familiar to attacking once one function-based coin. Every party attacking once. I think it's way more complicated when you have many-turn protocol. What is many-turn protocol? Every party sends many messages. So think about n square majority, rounds majority. In rounds, every party sends n coins, like each party sends a coin, then all parties send the coin again and again and again until you take the majority. So in this protocol, because there are n square coins, and each message is only one coin, there's no big jumps. The biggest jump is 1 over n. And if you're attacking square root of n times, you should accumulate many jumps to make the bias. The problem is that protocol might punish people that parties that deviate from the protocol. Namely, for instance, if you send super logarithmic number of consecutive 1, then the protocol say, ignore this guy, he's a cheater. Okay? And then you are dead. So again, what started about many terms protocol is because you cheat many times, you should disguise yourself. You cannot bluntly attack, because if you bluntly attack, the protocol description identify you as a cheater and expel you. So this is similar to what happened in coin flipping to begin with, right? In the very base simple two-party coin flipping. For very different reasons. There you didn't want to bias distribution when you apply one function. Here you don't want to bias distribution because you don't want the protocol prescription to expel you. But different attacks, so different attack, that's one to bottom line, very different attack, but the rationale is the same. You have to attack gently, okay? If you attack gently, you act almost like the protocol, the protocol output 1 anyhow. So again, you just should be that it's going to be the 1. Because you like 1, don't totally ruin the protocol. Act like it's an honest execution that state to be led to 1. Okay, so let me conclude. So coin flipping, at least to my opinion, are amazing objects. Studying them enrich our understanding of computation and interaction. Really, it's a great opportunity to learn new things about interaction, learn new things about computation. But it requires gentleness, okay? It's unintuitive because, as a mathematician, as a cryptographer, when you see an attacking opportunity, you want to take all the money from the table. You say, no, take just a bit, You have another opportunity, then you take another bit. It takes a while to get used to things like that. Some of the questions, first, much work can be done to simplify current proof, improve some of them. Want to skip that. But more generally, prove lower bound. It's very tempting to prove upper bound, and that's why it's easier. I'm not saying the lower bound is as important as where one is sitting as public key cryptography, but they are very, very important. Okay, lower bound really the complementary picture of the upper bound is lower bound, and as a community, it's very important for current and future research to prove lower bound, and it's also a lot of fun. Thank you.
Can you say a bit more about the optimal resilient functions and the non-adaptive full information?
Non-adaptive, I not think Andre will tell you a way better result. I think you should took how it call not juntas. How would you call this protocol? The tribes function, etc. There's many non-trivial functions that you made if it's single term or many term. In the many term, I can tell you, you recursively select committees. So you select committees using the light beans of Fage, and then the committee select a smaller committee, etc. This is the for many term. If you want every party to speak once, speak about function, then you take tribes. So.
Does the theory change in any way if we only want to bias in one direction? So if you and I fight about the car, you want to bias to 0, I want to bias to 1. The other direction, we don't care.
Maybe you cannot, some protocols are resilient for attacking from one direction. One direction take n parties. If it adaptive, there are protocols which are resilient to one direction but not resilient to the other.
But so does it still imply one-way function, etc., etc.? Do this?
No, I think about. Okay. You speak about full information coin flip, or which kind of coin flip? For one function based coin flipping, our protocol attacks to both directions. We have attacked to both the one. Yep.
So moving kind of beyond coin flipping, do you have any thoughts if we talk about more general protocols and the gap between what an efficient adversary and an information theoretic adversary can do? Assuming there are no one-way functions?
No, but it's somewhat related. Somewhat related, not really, but somewhat related. I think go below the one-way function world, go to like public key or especially OT kind of worlds, correlations. We don't understand correlation. Sorry, some of us better than others, but still, we don't understand computational correlation. We really don't understand it. We don't have amplification theorem, neither lower bound, nor upper bound. Everything is untimed. So, computation correlation, how does it relate to information theoretic correlation? Can you purify it? Is there a 0-1 law? I spent too much time trying to prove result. This mostly fail. By the way, proving lower bound, as you know, you mostly fail. So, but this is like what I consider maybe the biggest question is tension in cryptography is understanding. Start with two-part code.
I think it's very interesting, but I was asking in the other direction. So somehow your results give me the feeling that for this task of coin flipping, if there are no one-way functions, then an efficient adversary can do essentially as well as an information theoretic adversary, but it's very specific, right? Like you're using the structure of the problem of coin flipping. And do you have any thoughts on whether, can we say this more generally for protocols, for constant round protocols? Maybe we can.
That's an answer what I know.
Okay.
So I don't know. Many protocols can be cast as coin flipping. Okay, this is what good about coin flipping. Many other protocols are non-coin flip, hide coin flipping inside there. Like you can choose the input of the parties at random, and then it's a coin flip. So the low bound coin flip is very general. Other than that, I don't know. Probably Yuval knows, but I don't. Yes.
It seemed like if we wanted to break the 1/square root of R kind of threshold, we needed the OT, but we also needed to give one party the ability to attack while the other doesn't. So you have this asymmetric kind of behavior. Do we know how to break this this barrier without this asymmetric behavior?
Yeah, I mean, even the protocol that we seen before, the Moran et al. Protocol, you can give the difference value on the other part, it wouldn't change much. So the protocol that we've seen, no, it will take me ages. So there, you can, without changing much, you can give this difference value also to Alice, and then be symmetric in some sense. Yeah, so both Alice and Bob can attack to get one of them.
Shall we wrap up? So let's thank Iftach again. So now the lunch break, and we continue at 1:35 p.m.
And the broadcast